Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the second video of week 10. In this video I want to present and prove a lemma which will be needed for the proof of the general case of theorem 538. That was the theorem about the Nash equilibria in infinitely often repeated games, the Folk theorem. So this lemma is about the geometric series and certain additional ingredients there. So the natural numbers are denoted by n. They start at 1 in Germany. And if I want to start at 0, I write n with an index 0. So these are the non-negative integers. So now we fix a natural number n, and we fix n positive real numbers, which each are smaller than, less or equal than 1, and such that the sum is equal to 1, the lambda 1 to lambda j and n. Now recall that for any positive number between 0 and 1, the geometric series, the sum of all the powers delta up to k for k non-negative integers, is a convergent series with the value 1 divided by 1 minus delta. And now I come to the statement of the lemma. For any delta which is sufficiently close to 1, namely bigger or equal to 1 minus 1 over n, a partition of all the non-negative integers into n disjoint subsets I1 to In exists, such that for each j in 1 to n, the sum over the powers delta up to k for k in the subset ij is equal to the real number lambda j divided by 1 minus delta. So 1 is the sum of lambda 1 plus lambda, so all the lambda j's, and 1 divided by 1 minus delta is the sum of all the summands lambda j divided by 1 minus delta. And what the lemma says is that we can split the index for summing in the geometric series into n subsets, such that the subseries for these indices of the geometric series have precisely the prescribed values lambda j divided by 1 minus delta. So this is part A of this lemma. And before coming to proving it, I come to part B, which is a refinement. So in part B, we again fix a natural number n, and again we fix n positive real numbers which are less or equal to 1, such that their sum is equal to 1. Yeah, and now I'll come around into the statement. For any delta which is positive and sufficiently close to 1, so it is bigger or equal than 1 minus the minimum of lambda 1 to lambda n, a sequence j of L for L in 0 of numbers j of L can be constructed. So this is a sequence just where we, at each index L, we choose one of these numbers 1 to n. So we jump between the numbers 1 to n infinitely often. Such a sequence can be constructed such that for any finite positive number big N, natural number big N, the vector of the partial sums of the partial index sets for L less or equal n and j of L equal to 1 or 2 or 3 or n, the partial sums approximate the partial vector 1 minus delta up to n divided by 1 minus delta times lambda 1 to lambda n very well. So here one has to recall that we have also the finite geometric series. So the sum of L from 0 to n minus 1, delta up to L, this is 1 minus delta up to n divided by 1 minus delta. So now we want more than in part A. We want also that in all the intermediate steps, the sums approximate very well the decomposition of this number. So the number 1 minus delta up to n divided by 1 minus delta is also decomposed into pieces, namely lambda 1 times this number until lambda n times this number. And we wanted at each step the partial sums for j equal 1 to n approximate these numbers very well. So here it's written precisely what I want. So we look at some difference for fixed j in this fixed for any j in this fixed number n. So j is some number between 1 and n, and the number big N is fixed. So the first part in this difference here is the partial sum for L less or equal to n, such that j of L is equal to j. And the latter part is now this part of this of the value of this finite geometric series, namely the part given by lambda j. So these differences are interesting now. They are not all positive. Downstairs here, as you say, that their sum is equal to, you see here the sum is equal to 0. So some are positive, some are negative. And we want that our sequence j of L is constructed in such a way, such that at each step big N, the sum of the absolute values of these differences is sufficiently small, namely smaller than 2 times n minus 1 times delta up to n. So in fact, we will get even more. We will get even that also each single difference, Jn, is less or equal delta up to n. But here this is only an upper bound. Here I don't have absolute values. So this holds also. So yeah, and I remark again that the sum of these differences is equal to 0. You see it here downstairs, because the sum of the first parts is just this finite geometric series, and the sum of the later parts is the sum of these lambda j, which is equal to 1, times the value of this finite geometric series. So we get finally 0 here. So this is the result of this is part B here of this lemma. It's the refinement of part A. Part A looks only at the limits, but part B looks also at the intermediate parts of the geometric series, at the parts of the finite geometric series at each step n. So, but now let's look again for a minute at part A here. So now first I want to prove part A. This will be a preparation for the proof of part B. So we want the decomposition of n0 into these n disjoint sets, such that the partial sums over these index sets give these partial values of 1 divided by 1 minus delta, namely lambda j divided by 1 minus delta. So now I come to the proof. This partition of the non-negative integers will be constructed inductively as the limit for L going to infinity of partitions of the first L numbers. So in the partition there, I call the subsets I1L until INL for any non-negative integer L. L equals 0 is the empty partition of the empty set. There is nothing to do. So induction. So I have an induction hypothesis. I will do it in such a way that for any L, the partial sum will be less or equal to the limit, the desired limit value, lambda j divided by 1 minus delta. So, in fact, this is necessary because I can never go down. If the value is at some point too large, I can never go down because I will always add something. So I must stay below this limit value, this desired limit value. So now, the beginning of the induction is empty. For L equals 0, I have nothing to do. And now I have to do the inductive step. So for any fixed j, the sum of all these, so I look at the sum of the differences. These differences are all non-negative by induction hypothesis. So these differences here, they are all non-negative by induction hypothesis. And the sum of these differences can be calculated. The first part is just 1 minus divided by 1 minus delta. And the second part is this finite geometric series until L up to minus 1. And that has this value here. So at the end we get here for the sum of these differences the value delta up to L divided by 1 minus delta. So now the sum, all these differences are non-negative and their sum is equal to delta up to L divided by 1 minus delta. That means that there exists at least one index such that the difference for this index is bigger or equal than 1 over n divided times this term. So here 1 over n times this part is 1 over n of this sum of the differences, and at least one of these differences must be at least as big as this value. If all are smaller, then also their sum would be smaller than delta up to L times divided by 1 minus delta. So now we observe that delta was supposed to be bigger or equal 1 divided 1 minus 1 over n. So and this here translates to this inequality. We just have to put 1 over n on the other side and delta on the other side, and then divide by 1 minus delta. So now if you look again here above, upstairs, then this tells that here that this is bigger or equal to delta up to L. So that means that for this special index J of L, the difference of our desired limit value and of the partial sum of the geometric sum, the difference is sufficiently large, it's bigger or equal than delta up to L. And therefore I can choose choose the partition for the next index L plus 1 such that the set with index J of L gets the L and the other sets get nothing new. So in the next step I have to put the number L into one of these n sets of the partition, and I can choose this as J of L because there the difference is sufficiently large. I'm still allowed to add delta up to L. The new difference will still be non-negative. So this finishes then the induction step. That means we can go up with the L's and then enrich all our n subsets of the partition. And at the end we get then a partition of the set of all non-negative integers, and we get then again still non-negative differences. But then at the end the sum of the differences is equal to 0 because both parts give the value of the geometric series. So, but all differences are non-negative, so therefore all must be 0. So in the end we have the equality which we wanted. So this is the proof of part A. Now we have to go to part B. Let's just recall what we want. So in part B we want almost the same, but we want more. We want even a better control of this construction in the intermediate steps. We want that in the intermediate steps the values of this intermediate partial sums approximates very well the intermediate value of this, or the value of this the parts of the value of the finite geometric series. So we have to be more careful with our construction. So here it starts. So I could also talk about this partition into these subsets I1 to In, but here I prefer to talk about the sequence J of L. So we have a sequence of numbers which jump between the numbers 1 to 3 to n. And we will now be very careful in constructing this sequence. So suppose, again inductively, that for some natural number big N, we have already constructed the sequence J of L for L smaller than n, such that the same condition as in the proof of part A is satisfied, namely the desired limit value is bigger or equal than the intermediate part of our sum. So this is the part of the geometric sum where L is smaller n and where j of L is equal to the number j. So that's the same condition as before, but now we need more. We have to be more careful than before. Now we will construct the next index j of n of our the next member of our sequence j of n as follows. So now we consider not just these differences between the limit value and our finite partial sums, but more precisely we look at the difference of the finite partial sums, which is written here, and now the desired value of the intermediate value for our finite geometric series. So these differences will not all be non-negative. Some will be positive, some will be negative. And you have seen in the formulation of part B already that the sum of them is 0. So therefore they cannot be all of the same sign. And now the j of n is just chosen as the index of a minimal difference, where I do not mean that the absolute value is minimal. I really mean that the number is minimal. So it is a negative number, probably. So minimal here not in the absolute value, but on the whole real axis, the minimal number. So the sum of these differences is 0. Therefore, this minimal difference is definitely less or equal to 0, very probably smaller than 0. So again, let me stress this minimal doesn't refer to the absolute value of this difference, but really to the real number. So I will choose the smallest real number. We'll choose j of n such that this difference takes the smallest real number. So now I will again calculate this this difference, this minimal difference, and estimate it. So here I take now this is a different one. This is still the limit value, the desired limit value here. And this is a partial sum for j of L equal to j of n. And so, here, this is one part of this difference upstairs, but this is the limit value. And now I can also write it as a difference upstairs, here, this difference for j of n. But then here I have to, of course, to replace this limit value by the difference of limit value and this value here. And this is then the number here. So then I keep this number which we have here. This number, I keep it. And the difference, now I can estimate by 0 from above. I know that this difference is the minimum one, so it is less or equal to 0, so I can estimate it by 0. Then I get just the first term, and here the first term can be estimated by delta up to n, because by a similar calculation as before, here our assumption that delta is here gives us also this inequality. So lambda j up to n divided by 1 minus delta is bigger or equal to 1. Therefore, this whole difference here of the limit value minus our partial sum is again bigger or equal to delta up to n. So this is essentially the same result as in the proof of part A. Therefore, the sequence works as an A, and we can now choose so now we have already chosen j of n in this way, and now we see that also the difference of this value here minus this value plus delta up to j of n is still non-negative. So this part works as in the proof of part A. So in the vector by the proof of part A, we know that this vector of these partial sums that tends for n going to infinity to the partial sums of the geometric series, to the desired partial values of the geometric series. So, but this was just somehow the same point as in part A. Here we want more. We want also that the differences, the intermediate differences to the intermediate values, stay as small as we claim. So this still has to be proved, this estimation. So the new point of part B still has to be proved. Our construction of J of n was a little bit different than from before, but it works again. But we have still to prove the new statement about that these differences diff Jn are sufficiently small. So the minimal one is less or equal 0, because the sum of all of them is 0. And now if I add delta up to n, I can now calculate also the new difference for n plus 1. So the new difference for n plus 1 is equal to the old difference, but they have to replace the old intermediate value for the finite geometric series by the for big N by the corresponding value for big N plus 1. And one sees that here one has to add precisely this sum here. So, and now as we just have seen here, it was written here. We can here in the right hand side we can replace lambda j of n divided by 1 minus delta by 1, and then we get this part here. And of course the difference then can be to the first summand is then delta up to n plus 1. So by a similar calculation for the other differences, for the indices j not equal to j of n, gives us a similar estimation also for them. So for all of our differences, we get this inequality. And the similar calculation, I want to carry it out now on some other slide on this page where I sometimes make extra calculations. So it is here. So here it is. So for j not equal to j of n, I want to prove inductively that this difference for index j and the fixed number n is less or equal to delta up to n. In the manuscript, I have just written down the proof for j equal j of n, and here I'm writing down the proof for the other j's. So now I want to prove inductively the next step, that the difference for j and n plus 1 is less or equal to delta up to n plus 1. So this difference by definition is the sum of these, the sum of the geometric sum for L smaller n plus 1 and L with j of L equal to j, minus this intermediate term here. Maybe let me try to make it with colors. So this is the, oops, it doesn't work here. No, it doesn't work anymore. So this is the difference, and the difference for j of up to n, there one has to replace the second term which we have here. We have to replace this term here now by this term, and then we get as a difference term this term here, which we had already seen. So then this first part here is equal to the difference j of n, and we get in this as the second term. Oops, I didn't want to erase here. Oh, I'm sorry, I erased quite a lot. I didn't want to do that. Jn so in the first term here, this term now can be estimated by delta up to n, and the second term we can again replace this by 1. It's bigger or equal to 1. It's bigger or equal to 1, and here's the minus sign. So this is negative, so we can replace this. And then we get the same calculation as before. We get delta up to n plus minus delta up to plus delta up to delta 1. So we get again here delta up to n plus 1 that we wanted to prove. So now I return to the other manuscript. So I try to explain here the similar calculation on this other page. It is also an inductive calculation. So now we get this for all j, that the single difference is less or equal to delta n. Here remark that I didn't put absolute values, it's just an inequality for real numbers. So it's just an upper bound, not a lower bound. But easily we get also a lower bound from this. Namely, we have some of these differences are negative. Here we have less or equal to 0, and here we have bigger or equal to 0. And the minus the negatives is equal to plus the positives, because the sum of all of them is 0. So we get the equality here. And the positives one, there are at most n minus 1 of them. They are together less or equal to n minus 1 times delta up to n. So and the sum minus the sum of the negatives one takes the same value. That means the sum of the absolute values is at most the double of the sum here. That's what I have written here. So that now finishes the proof of this part B of the lemma 540. So the first half was almost equal to the proof of part A, but we had a slightly different way to determine this, the next element of the sequence j of n, which is namely by looking at this differences for the intermediate sum. And then we had to do some additional argument to show that these differences stay all small enough. But these inequalities worked. So now this finishes the proof of lemma 540. And let me say again that this is in some sense my lemma. I have not found something sufficiently similar in the literature, especially not the part B. Probably there is something, or certainly there is something which can replace this in the papers of Fudenberg and Maskin, but I haven't seen this. So this is my lemma. So in the next video, we will apply this to the proof of the general case of theorem 538 on Nash equilibria for infinitely often repeated games in normal form. Thank you very much.